I will present Consert experiment and measurements, and in fact I will talk about preliminary result. And but I will start by describe Consert in a really fast way. Consert is a bistatic radar, which is on the orbiter. This is Consert antenna, which is also on lander. And on orbiter and on lander, we have transmitter and receiver. Consert works as transponder, which means the signal is sent from the orbiter to lander, and lander responds. We send 90 megahertz signal with 10 megahertz bandwidth. And this is some kind of sketch how Consert works. But I will show a short film describing how it works. This is the first images. You can see the Consert antenna, if you can see really, yes, I can see from here. The Consert antenna, which were open when landing gear were opened. And now, could you start this? Yeah. Well, okay, let's start. Okay. This describes how Consert measured. It's really a short movie, but in fact Consert works like that also during the occultation measurements, which means that lander send the signal to the the orbiter send the signal to the lander, and lander runs first. And this was the measurements. You should see here, the descent. Perhaps once again, it's really short, very short. And you see, this is some kind of ping pong, the signal sent from orbiter to the lander is transferring, and here we are plotting the measured distance during the descent. Okay, it's done. Here are the photo images we just have seen, showed by Jean-Pierre Brink. You can see Consert antenna, if I see well here, yes, here is, and there is second one somewhere here. And what I wanted to describe, what we did during the FSS and during the descent. The Consert measurements were done during the descent, but we had to stop 40 minutes before touchdown because Consert perturbed Sesame, and Sesame had to measure first touchdown. Unfortunately, we stopped for the long period until the next planned measurements, which was planned at the Cite J, where we should go to the occultation. And we did not see really the flyby of the lander, and probably if you could see, we know now where lander is. But it was not the case, unfortunately. We ran after the Consert, starting at 7 p.m. until 4 in the morning. We have, during this, we start immediately. We start at 7 when we have been in occultation, not before what we planned to do, but Cite was not the same. And we finished still in the occultation. Then ESA asked to have the free measurements period to make a ranging between Consert and orbiter in order to do the triangulation to detect where lander is. And this is the distance between orbiter and lander. This is 0, and this is about 15 kilometers before touchdown. But this is theoretical distance, what was planned. And it was what was afterward calculated with optical method. And here is our descent measurements, Consert measurements. This is distance between the spacecraft and Philea, and starting from 0, we go to about 14 kilometers when we had to stop operations. And here is the measurements. The difference between Consert measurements and optical a posteriori measurements. And you see we have the error of the order of 10 meters. This is in the meters of the distance. And this error here increased, but I was taught by flight dynamics that optical measurements are some bias in the end. and they are now correcting this. Anyway, we have on Consert the, let's say, plus minus 5-10 meters of accuracy with the distance measurements. This is the signal during the descent, which was very strong at the beginning. This is logarithmic delay, 80 dB. This is the time delay in microseconds. It's 25 microseconds is the duration of our signal. And we are doing the measurements modulo 25 microseconds because we are using periodic signal. And this is signal. This is the signal just before we stop operation, and we started to observe the reflections from the surface. And this we, of course, will analyze and to model this and to understand what are the electric properties of the surface. Well, this is linear scale to see how is the amplitude. Previously was in dB. And these are the measurements of the maximum peak power of the signal during the descent. You see this variability here, which is due to the rotation of the orbiter. During the descent, the rotation period was about 8 minutes, and orbiter rotated. But what happened that in the end, you can see here, we made spectral analysis, but I did not show here, or will not show here. The period is changing. We don't know yet today the reason, and or this is the observational angle, or it is because the friction on the rotation reaction really changed, or I don't know what else. And here we have the measurements during the first science seconds. We observed we have the measurements during the whole this orbit, which is about from 7 in the PM to 4 in the morning. And when the green color show where we have strong signal to noise ratio, the blue also where we have the strong signal to noise ratio, the red one show where the signal to noise ratio is bad. And in order to extract the signal, we will have to do some special processing, let's say take out the spurious line, etc. But we will certainly not determine or measure signal during this whole period. Probably in this area we should determine probably this. And what you see here, this is if we suppose that lambda is in this position here, we will go through the whole this head, inside the head, what I'm saying, to observe this signal. And in this part, we go through this part of head, which makes our estimation, we probably went about through 800 meters, perhaps 1 kilometer inside, not more. And the red line show here the signal corresponding to part of this orbit, which means the signal went through the head, after through the space, and go into the body and went out through this path. And this is the signal which we, unfortunately, probably will not be able to extract, perhaps partially. And this is a plot of the signal at the beginning, where we have here is the delay, which means the delay, each step corresponds to 100 nanoseconds. And to step, because we have here, this is the delay by redress. But anyway, we have this is the power of the signal in time measured as function of sounding. Every sounding was every 5 seconds. Discover about 40-45 minutes of the data. We know that you have data here also. And you see that signal is extension of the signal is of the order 10 steps, which means that's 1 microsecond. I will show after the more precisely. This is the end period. The time here is in the minute. And you see, I changed the scale here in order to show what is the dynamic of the signal, what is the width. You see the signal is relatively narrow here, and after it's spread out, which is perhaps due to some kind of multipath propagation. You can see here, I plot few examples of the signal. You have this, in dB scale, the signal to noise ratio is relatively low. You have very sharp arrived signal, and there is some increase in the width here, but at the lower level. The same you see here, and on this is later where we have strongest signal. Here signal to noise ratio is about 30 dB. And we can see multipath propagation, which means that you have different paths propagating inside the comet, which you have to interpret. And the last one is very strong now, it's almost at the end of the experiment, and you have really multipath propagation, and you here see additional path. What I don't see here, but perhaps it's only the example, I don't see the spreading due to the scattering inside. If you could have a lot of small parts of the order of meter or 2 meters, with change of the electric constant, we should see volume scattering. It seems that I don't see here, but these are only 3 examples. We have analyzed all the things. And this is linear scale. You see how the signal is the same signal in the linear scale. You can see here what kind of a dynamic we have. And here I replot once again, you know, what we see. Certainly we have signal going through the comet on this side, on this side. And here is the other part we should see, but we have to process, and I don't know how much we'll be able to obtain from this. And as it was said previously, we were looking to determine the landing site, because we need to know where is the lander. Of course, today we have, this was the first estimation, which we used these 3 ranging measurements plus the measurements through the comet. The diamond here show our first estimation during the night from 12 to 13, where we announced that lander move about 1 kilometer, even more. And this is very big area, of course, because we don't know the properties of the comet, which we assume something. And we're using the ranging, we determine this area, and in the end, using the better a posteriori orbit prediction from the flight dynamics, we determined this small area, and we hope, I believe, unless a posteriori orbits are not yet completely correct, we have to be here, because our measurements are with 10 meters, let's say, accuracy. It's hard to imagine where we are somewhere far outside of this region. This is what I am thinking. And I have to add the flight dynamics made different estimation using our measurements, and they find about exactly the same area. Okay, thank you. At the end, I would like to thank ESA teams, ESOC team, flight dynamic team, and SGS team, and Philea teams, LCC and SONG, for very good collaboration, and we worked together a few nights in order to find where lander is. Thank you.
Okay, the paper is open for questions. Please step to the microphone.
Oh, can I shout?
You can shout. Yeah.
From what you know about where that dinosaur egg material was, did your signal transect that at all, can you say?
So Holger had.
Holger find.
So Holger had this image with the what he called the dinosaur eggs.
Yeah. Okay. I don't know, because I don't know, and firstly I don't know where is comparative to our signal, and secondly I show 3 cases of the signal, and normally with this large scattering, as you know, you should have a large Q, and but of course I don't see this kind of Q on these signals. Perhaps you will see if you go through the region where Holger showed, but if interior should be like that, and this X should have a different really dielectric constant, we should see large Q. If not, I don't understand.